1 over 1 plus L. Alright? And how does disturbance relate to your output Y? So Y is the sensitivity of S times B. Okay? So it's very obvious that in the area of disturbance attenuation, if your S is small, okay, the smaller your S, the more the disturbance are attenuated, meaning reduced at a certain frequency omega. Okay? And how do you keep S small? Because S is 1 over 1 plus B, okay, it's small if L is, S is 1 over 1 plus L, S is small if L is large. Okay, very obvious. Okay, and so it tells you that in those regions, those frequency regions whereby you need disturbance attenuation, okay, in frequency regions whereby you need to eliminate disturbance, you need to make L very large. So it tells you that because L is C times P naught, in those regions you need to make a controller gain very large. Okay, however, this is limited by plant capacity. And in the area of bandwidth, alright, realistically you can only make L very large over a limited frequency band. Okay, because any functional control system has a limited range of functional frequencies. Alright? And this is what I call bandwidth. And we use B or sometimes BW to denote bandwidth. Okay? We will look at the bandwidth of a functional system and also what we said earlier on about crossover regions. Okay? This is a part of the sensitivity function, the complementary sensitivity function. What is extra? So now you see a B here for bandwidth. Okay? Basically what we are telling you is if you're operating the system, okay, you ought to operate in this region. Omega from 0 to B. Okay? Alright, does it make sense? Because if you look at the sensitivity function for omega from 0 to B, S is small. The complementary sensitivity function for omega from 0 to B, T is 1. So you have perfect Kalman tracking, okay, and very good disturbance attenuation. Okay, so I need to deal with the measurement noise on a separate case with other measurement sensors. Okay, and what about the region around the bandwidth B? And we did discuss that this frequency region around bandwidth B is so-called the crossover region, remember from our stability criteria. And in this vicinity around B, you want to avoid picking of S and T. Alright, otherwise you will magnify your disturbance. And also a measurement. Okay, so this is for sensitivity functions. How sensitivity functions okay, it takes your bandwidth and disturbance attenuation. Okay, next, complementary sensitivity function, T. Okay, recall that we said that T will come into play for the command response tracking and also for the measurement noise. Alright, so in terms of command response tracking, right, Y is T times FR. Okay, let's see that for the linear region in the bandwidth, T is approximately 1. Alright? Okay, we have very good tracking because the command response is close to 1 up to this bandwidth, 0 to omega. Alright? And if you actually require a different command response to this, alright, if you like something else, what you can do is you can actually adjust the pre-filtered F in front of the reference, okay, to change the command response. Alright, so complementary sensitivity function T relates to both the command response and also the measurement noise. Okay, so in the area of measurement noise, say that T determines measurement noise activity, and at high frequencies, T should decrease as quickly as possible. Alright? Okay? At low frequencies, your T is very close to 1 or dot. So this emphasizes the need for very good low noise sensor at low frequencies. Okay, so other than Y, D, N, and R, F, there's another signal in this entire system called U. Okay, control signal. So we can also derive a system function, SU, and a control sensitivity function in this manner. Alright? So if you write out the relationship between the output, common response, disturbance, and measurement noise, so Y is Cp not over plus Cp not FR. Okay, plus 1 over 1 plus Cp naught times D, disturbance, minus Cp naught over 1 plus Cp naught times N for measurement noise. Next, you derive your error E, which is FR minus N minus 1. Okay, and you know that U is C times E. Okay, and derive that U is C times FR minus C times N minus C times 1. Okay, and how do you move from here to here? Okay, this is this. Alright, so U is C times E. Okay, so U is C times FR minus C N minus CY. Alright, all you need to do is put the values. Okay. For Y, so substitute Y into this 3 terms. Recollect them and simplify. Okay, so in the exam, you can ask to derive control sensitivity function SU. This is what you do. Okay, and the next thing you note is SU, alright, is C over 1 plus Cp. Okay, SU is C over 1 plus Cp. Okay? C over 1 plus Cp, and recall that your complementary sensitivity function T is Cp over 1 plus Cp. So your complementary sensitivity function T is Su times P. Okay? So requirements on SU, the control sensitivity function, can be translated into requirements on T. So what do you want for input control signal U? Okay, you want to avoid overly large SU because you have limitations in your control signal. So it also tells you that at low frequencies, okay, your loop gain should be high for low sensitivity and T is equal to 1. Alright, at low frequencies, if you have this, you may need to exceed of high capacity. And at high frequencies, your SU should increase as fast as possible because SU has to follow the same relationship as T. Okay, otherwise your measurement noise will affect input. Okay, so it's still relatively consistent. Okay, the other thing you need to know about SU, okay, is also the fact that there could be right-hand pole zeros in SU. Okay, so we derive that SU is C over 1 plus Cp naught. Alright? So this is just okay, now over 1 plus L times of P. Alright, so if we can derive this with L over 1 plus L times 1 over P, you know that when L, okay, is much bigger than 1, effectively L over 1 plus L is 1, and SU is approximately 1. Okay? And if your P, which is a plant, has unstable zeros. Okay? 1 over P is unstable. Because unstable zeros in P will translate to unstable poles in 1 over P. Alright, an example is this. So if P is K times S plus 1 over S plus 1 plus S plus 2, S minus 1 plus S minus 2, 1 over P, okay, you can see that the unstable zeros are now the unstable poles. Okay? So basically what I'm saying is unstable zeros in P, alright, are now unstable poles in 1 over P. Okay? And these unstable zeros will actually limit your frequency range of operation, which is a value. So we say that SU, the control sensitivity function, may only be made equal to 1 over P up to a certain frequency range. Okay, and the frequency range is equal to the magnitude of the plant right-hand pole zero, the smallest. Okay, so this is a summary of what we are going to talk about. Okay, basically what we're saying is L is Cp, and if Cp is very big, SU is approximately 1 over P. And if they are unstable, zeros in P, 1 over P has unstable poles. So operation of your system is limited in terms of value from 0 to B, where B is the smallest right-hand plant, right-hand pole 0 plant. Okay, B is smaller equals to the smallest plant right-hand pole 0. Okay. Alright, and when you actually have very high load gain, alright, what we have learned previously all still applies, right? So it has small, T is supposed to be 1, T is 1, take the loop disturbance attenuation, alright? Any questions? Okay, there's only one main point in this entire slide we ought to remember. That is, we have already derived that SU, okay, is C over 1 plus Cp. Alright? SU is C over 1 plus CP. So then you can derive that if L is much bigger than 1, SU is equal to P. Okay, if P, which is a plant, has unstable zeros, okay, 1 over P has unstable poles. Alright, so the operation is limited by the smallest right hand pole 0, or bigger 0. That's all. Alright? Okay, let's move on. Okay, let's move on. Is this okay? Yeah? So stability robustness is just a summary. We have already completed this. Okay, when you look at Doyle's stability criterion, this is just a summary. Alright? I will tell you that what are the requirements for robustness, performance, and when they have perturbations. What is the size of the perturbation allowable, which frequency range, and at crossover, you have to be careful because you cannot be taking an SNC. Alright, this is what is actually more important. The next slide for performance robustness. Okay, so now we're telling you that if you want to look at performance robustness, you don't just look at S and T. You also look at SU, control sensitivity function, open loop response. Alright? Because the control sensitivity function and the response depends on S and T, we need to consider the effect of perturbations on S and T. What does it mean? Okay? For those who are interested, please refer to page 13 for feedback notes. And this is this. I'm going to explain to you what it means. Okay, I'm going to take you through what it means. Okay. So you have SU, which is C over 1 plus CP naught. Yeah? Okay? The Y over R, which is your overall response, is your constant. Complementary sensitivity. This is C over 1 plus. Okay? Alright? Next, what we're trying to say is because S naught was this, and T naught was this. If there is now a change in P naught, okay, how will that affect my S naught and how will that affect my T naught? Okay, if there's now a change in P naught, how is that going to affect my S naught and T naught? So how do you do that analysis? So you say relative change in S naught U, so relative change in P naught. Okay, is this delta S naught over S naught divided by delta P naught over. Okay? And this is delta S naught over delta P naught times P naught over S naught. Alright? Okay? And in one of the past exam papers, they tell you to write that this is equal to minus okay? Obviously some of you may be laughing. Say what's the extra information? Okay, what you need to do now is because S naught is 1 over 1 plus Cp naught. So effectively you differentiate 1 over 1 plus Cp naught over P naught and you multiply with P naught and S naught. So how do you do this? Your S naught is bracket 1 plus Cp naught inverse, right? Alright, so how do you differentiate this? This is negative 1 plus Cp naught times 2 times C. Alright? Times P naught over S naught. Okay? And S naught is this, so you times P naught 1 plus C. Alright? And you end up with Cp naught over 1 plus Cp. Okay, so this is exactly minus P naught. Alright, it's just a differentiation. Okay, I'm sure you can do this, right? It's just a differentiation. S naught is bracket 1 plus Cp naught bracket inverse. So you differentiate S naught with respect to P naught. You have negative of C minus 1 plus Cp naught to the power minus 2. Correct? Times P naught times 1 plus Cp naught. This is 1 plus. Then I have negative of. Okay, what about the relative change? Relative change in T naught due to relative change in P naught. Okay? So how does the complementary sensitivity function change? Similarly, you do delta T naught over T naught over delta T naught. Okay, so likewise, Cp naught okay, I'm going to leave this as an assignment for you to do, which is just to differentiate this. Right? So what I have is delta T naught over delta P naught. You differentiate this with respect to P naught. Okay? And then multiply that P naught over. Alright, we prove that this is S. Okay, try and do this so that if we come out in the exam, we know how to do this. Okay, so let's continue. review of design requirements, nothing much. It's just a summary. Okay, so about sensitivity function S, be small and low frequency for Q, disturbance attenuation, command response, and robustness of T at low frequencies. Okay, because a change in a change in S relative to a change in P is equal to negative of P. So S has to be small at low frequencies to achieve robustness of T at low frequencies. Alright, the complementary sensitivity T, okay, a relative change of T with respect to a change in plant is equal to S naught. So it has to be small at high frequencies to prevent a loss of robustness of T of S at high frequencies. Okay, so just add this of T, this of S. And the crossover region, you want to avoid peaking of S and T. Okay, to prevent large disturbance sensitivity and measurement noise. Okay, 3 more to go. Now we'll finish early today anyway. Okay, so 3 more slides to go. Problem A. Alright, we say that the feedback system design can be seen as a process of loop shaping. So loop A, L is CP, right? So we're trying to shape L. Okay? Performance and robustness requirements result in certain specifications on your sensitivity function and your complementary sensitivity function in both high and low frequency regions. Alright? Because S is 1 over 1 plus L, T is L over 1 plus L. Okay, and your loop, your Nyquist loop L is CP. If you have bounds on your S and bounds on your T, okay, remember your law stability criterion, you actually have stability criterion bounds on S and T. Those relate to bounds on L. Okay? You have requirements on S and T for robustness and performance response. So there are also equivalent requirements on L. Because S, T, and L are all related. Alright? So we tell you that okay, there's a lower bound for low frequencies and a higher bound for high frequencies. And in this, there are some allowable phase functions. Because in terms of magnitude, there are also phase bounds. Okay? And in a crossover region, we want to try as much as possible to constrain the phase to avoid running into stability issues. Okay, just appreciate this. And the crossover region, the more closely the Nyquist of L approaches -1, you understand that. The more closely L approaches -1, the vector margin reduces, so Sm is small. When Sm is small, S is large. Sm is inverse S. Okay? If your plot of L approaches -1, your plot of 1 over L also approaches -1. Okay? And then your vector margin Rn is small, and hence T will be large. What's the inverse relationship? Okay? So to avoid peaking, you need those stability margins. Alright? Why do we write all this down in the slide? Are they important? Yes, they may be. Because if you look at the past exam questions, you are required to answer in complete statements. Okay, about the importance of why you want to avoid peaking in crossover regions. Okay, and the importance of how stability margins relate to avoiding peaking in sensitivity functions. Alright? Okay, so are there any questions on this? No? If there are no further questions, see you again.